Good afternoon, everybody. I am very happy to welcome you all to today's Copy with Curiosity for the lecture titled Discrete Charm of Geometry. This monthly lecture series, started almost 2 years ago, has become very popular. Many renowned scientists have delivered lectures in this series. Today, we have a distinguished scientist, Professor Alexander Bobenko from University of Berlin. A hearty welcome to you, sir. Jawaharlal Nehru Planetarium is a unique institution engaged in dissemination of science amongst public and students. Over 300,000 visit planetarium for our shows and to our science park. A unique feature of this institute is we have non-formal science education programs which run throughout the academic year. These attract students of wide age group from high school to undergraduate level. Copy with Curiosity is giving an opportunity to all these students and science enthusiasts an opportunity to listen to lectures and interact with eminent scientists. I once again extend a warm welcome to today's speaker and to all of you. I request Dr. Vijay Kumar to speak a few words about ICTS. Thank you.
Hello, everyone. Let me also welcome everyone on behalf of ICTS. As you all know, ICTS has been conducting these public lectures from the past 2 years approximately, and we've had a very nice loyal gathering and loyal following of people. So it's very heartening to see many of them. ICTS is also a unique institution. We seamlessly blend scientific research programs with in-house scientific research, also with public outreach, and this is an example of a public outreach program. So Professor Bobenko is visiting us as part of the Integrable Systems program that's currently happening in ICTS, and there are many participants from the program here as well. So we get distinguished speakers like him to come and tell us about various developments in science that's going on. So we really look forward to his lecture. So before he begins, I'll ask Dr. Chowdaiah, the former director of the Planetarium, to hand over a memento as part of ICTS and the Planetarium. So let me request Professor Amit to introduce the speaker.
Okay, welcome again, third welcome of the day. So Professor Bobenko did his PhD from Russia in Stricklau Mathematical Institute in mathematical physics. And then he moved to Germany on a Humboldt Fellowship to do his postdoc, and he has been in Germany since then. He is currently a professor of mathematics in Technical University of Berlin, where he heads the group on discretization in geometry and dynamics, a topic of today's lecture. His fields of interest include geometry, mathematical physics, differential geometry, and applications. He's currently giving lectures, actually he finished giving his lectures at ICTS on integrable systems last week, and he will be here for a few more days. We are very glad to have him. He also has various other interests, as I learned. He has directed and created this movie called Conform, and this is available from Springer, I guess, webpage, maybe Amazon, I guess, I don't know. I haven't checked Amazon. In his group, there was also another movie that was made that was exactly the same title as his talk, Discrete Charm of Geometry, which he will talk about also. So he's very much interested in conveying and discussing his research with general public, so we are looking forward to his lecture today.
Okay, thank you very much for the introduction. I really appreciate the public, that you are so many, and I have heard that people are quite different here, so I see some familiar faces of mathematicians, and probably there are people in the audience who know not that much about mathematics I'm going to talk about, so my talk will also be a sort of a compromise. So I will bring you to the front of modern research at the end of my talk, and actually the whole thing about this discretization is a very active area of research. So, but there will be not so many formulas in the talk. So I will try to do this as elementary as possible. So let me start with a picture of a surface which is probably the most famous surface in computer graphics. So if you do computer graphics, then you cannot avoid this model. And you can't avoid this picture. This is called the Stanford Bunny model. But in reality, the model looks like this. So what you see is a picture which is smooth, and it's a smooth surface, but the data are here. So they are triangles, they are glued together, and this surface we call a discrete surface. It's a polyhedral surface built out of small triangles, and it is supposed to be more or less the same as this surface. Okay, and then the question appears. Actually, what you would like to do is this surface. What is the best possible discretization? There are many possibilities, of course. This is a smooth surface, and you see here a discrete model. Here the model is even more discrete. And the question is, what is the best discretization? How to find the best one? And also, what is mathematical theory behind this? Actually, that's the original photo of the model. This is not virtual reality, it's a physical model. And this model was scanned and then became so popular in computer graphics. Finally, I will talk about discrete triangulated surfaces and also surfaces built out of quadrilaterals, and about similar problems in dynamics. The question is how to discretize, how to find discrete analogs. So we will discuss the idea of discretization, and the message is that the discretization should preserve essential structures of your mathematics and of your physics. So it should not be just random numerical discretization. It should be a sort of an intelligent discretization, and intelligent means, in this case, structure preserving. What does it mean, structure preserving? There is a lot of mathematical structures, a lot of physical structures in the models you are interested in. And the message is that these features, qualitative features, they should capture already at a discrete model. So you can recover then your continuous model when you come to a finer and finer discretization, when your mesh becomes finer and finer, but the discrete theory itself is supposed to be a solid mathematical theorem with theory, with theorems, proofs, and so on, as solid as the classical continuous theory. And last but not least, of course, that this kind of problematics, this kind of problems is important for applications. So an obvious application, which I have mentioned already, is an application in computer graphics. In computer graphics, your surfaces are not smooth, they are discrete. And what you should do differential geometry on this, for these smooth surfaces. But also there are other applications that are not, that are rather unexpectable. For example, applications in architecture, and I also will say a few words about these applications. So the main message is that the whole theory should be discretized, not just the equations. So this is a sort of a side remark that this kind of questions was also appearing not only in physics, not only in mathematics, not only in science, but in art. Yeah? So here you see two bodies. One is smooth, another one is discrete, and that's a famous homepage of Terpsichore by Salvador Dali, and you see that all essential structures are preserved. Okay, so as I said, the problematic is quite similar in geometry and in dynamics. So when you discretize in dynamics, then you end up usually with this field, which is called geometric integration. This is pretty well established, very practical, and in differential geometry, it appeared quite recently, essentially because now we have computers. That was one of the motivations, definitely, and it is called discrete differential geometry. Geometric integration is an old field. So I'm going to show you an original picture from a book by Newton, of his famous book, Principles of Celestial Mechanics. And you see, that's how he was describing motion of bodies in physics. And of course, during his time, the theory of differential equation was not yet well established, and so he had to argue kind of arguments. But this was also quite an intelligent choice of him, how to choose these triangles, how to build the corresponding theorem. So geometric integration is structure-preserving discretization in dynamics. And it's very important for practical applications. For example, if you, well, that's of course the best occasion to talk about celestial mechanics and about planet motion. Yeah, so in here. So if you, everybody knows that the motion is described by Newton laws, and they are explicit differential equations, and the only problem is how to solve them. So, but if you have many bodies, many planets, then you cannot solve these equations explicitly. You should solve them numerically. And then, of course, there are various methods. So you have differential equation, and then you can apply some direct methods like explicit or Euler method, solve this problem numerically. And then you see that the trajectories will look slightly, well, non-closed. And this means that the numerical error will accumulate and will destroy your computations if you are doing this for a long time. On the other hand, there are other numerical methods that are called symplectic Euler integrator. So also numerics, the same differential equations, but will look different and correct. And of course, we need such correct results if we are interested in motion of satellites and so on and so on. So, and this theory was developed in the 80s, so it's called symplectic and variational integrators, already well established. So this is a structure-preserving discretization in dynamics. So now let us look at another example which represents both geometry and dynamics. So you see geometric picture to the left, and you see dynamical picture to the right. This is a spinning top here, and that's the corresponding motion which we have all seen when we were children. Yeah. So what is important here, it's a motion of a rigid body with one fixed point under gravitation field. So what is important, important here are these dots you see here on the lines. So they, of course, mark your positions of the axis of the spinning top at some explicit points of time, moments of time. This picture is very closely related to this. So namely, let me explain you how to obtain this curve. This is so-called elastic rod. The geometry is quite simple. You consider a piece of elastic rod, and then you can bend it. There is bending energy, and you can twist it. So, and usually you have a combination of both. I will show you pictures later. And this is an example of an elastic rod. How to generate this elastic rod? So you take the axis of the spinning top, take the position of this axis, as a function of time and then integrate this function. So the velocity will become, okay, this axis will become the velocity of the motion along this curve. And so the motion of the spinning top generates you this curve, and vice versa, such an elastic rod generates you this spinning top. This is one-to-one correspondence, which is known as Kirchhoff correspondence. So time here corresponds to the arc length parameterization, parameterization by length of this curve. Okay, now what we have seen here is actually also a small movie, and it was a discrete movie. So in a movie, you see only, how many? 24 frames per second. So, and here, a map from one frame to another frame is just an explicit formula. So what you do here to generate this picture, you iterate a symplectic, so-called symplectic map. So there is no time in between. Only, it exists only at these dotted points, but it's distinguished discretization of this motion. And you see that this motion looks real, and it can run for 1,000 years, and still it will be correct. So the numerical error doesn't accumulate. So let me say a few words about elastic rods. So elastic curves minimize the bending energy. So you take a curve, go along the curve with constant velocity, and the acceleration is the curvature of the curve. And what you would like to do, you would like to minimize this functional, which is the integral of the curvature squared. So you would like to have your curve as straight as you can. So curvature is the acceleration of the motion along the curve with constant speed. And here, to the right, you see a page from a book by Euler, who has started research about elastic curves. And here you see the examples. For example, that's a physical thing. There is this curve, there is some gravitation acting at this point, and that's the form of the curve. And these are various discrete elastica. So the question is, what is a discrete analog of this curvature? So, and it turns out, first of all, what is a discrete curve? You have points and you connect them by straight intervals, and this is your discrete curve. So here in this picture we see two fragments of your discrete curve. And if the curve is straight, then this angle phi is 0, and phi describes your deviation from the straight line. So the question is how to define the curvature in this case. There are of course many ways and many formulas which you can imagine, and all of them, they will go in the limit when phi goes to 0 to the same continuous limit, k. But it turns out that the right formula for the curvature is this one, twice tangent phi over 2 of this exterior angle. And the discrete bending energy should be defined in this way. So logarithmus 1 plus kn squared over 4, where kn are the curvatures defined this way at all the vertices, and you sum over all the vertices. So looks complicated, that it's not quite clear how to get how to come to these formulas, and I'm going to show you how to do this. But it turns out that it's these are really useful formulas, and in this lecture I'm going to talk also about applications a lot. So there is a real application of this formula, of this energy. It's a model for a virtual paintbrush, and this formula is in a way implemented already in Adobe Illustrator or Photoshop. Yeah? So when you use this for drawing with your virtual paintbrush, then one part of the formula is this one. Yeah? So, okay, that's a practical application. Now, let us look how it works in reality. So what you see here is a real reality. These are two hands are not modeled. This is a photo. And this is a plastic piece of an elastic rod. So what you see here is a model made with this bending energy and twist energy, which I have explained to you already. So you see that the pictures look quite similar, and this means that, and they are non-trivial, so this means that you capture quite well characteristic features of the theory. One more picture about elastic rods. Again, you extremize the energy, which is the bending energy and twist energy, and this is the real figure, and this is the virtual one, so which also look quite similar. The elastic rods made in experiment and in simulations, they look quite similar. Okay, now I told you already about Kirchhoff kinetic analogy. So the axis of the spinning top corresponds to the unit tangent vector to elastic rod. So the axis is the same as the vector, unit tangent vector of your elastic rod, and time of the spinning top corresponds to arc length parameterization of your curve. So what we are going to do, we are going to describe discretization preserving the integrability. As you have heard, I'm participating here in the workshop on integrability. So I'm not going to explain you now what is the integrability. It lies beyond the topic of this lecture. But the integrability is something about equations which you can, that are complicated. You can solve them explicitly. And this is a very important structure. And you would like to preserve this structure when you discretize. So that's what we will do here. And I will try to explain you how it works. So in the picture we have seen this motion. We did exactly this thing. We have discretized the models, preserving the integrability, and this is a discrete Kirchhoff analogy, which gives you both discrete elastic rods and discrete spinning top. For the top, the time is discrete, and for elastic rods, you are considering a polygonal curve. And this is just some demonstration that numerically for the top, it works much better than standard Runge-Kutta discretization. Okay, so this is also science. So, and we see here so-called smoke rings. And this is about modeling of motion of smoke. So you can really do fancy things with this, but we are going to do mathematics, and then the machine which can be used, shown here, you can generate smoke rings, and then they evolve and they flow almost without changing their shape in space. Yeah? So this is well known, and you can try to repeat these experiments, but please not here. So, okay, so now let me explain you what is the mathematical theory behind this and how to describe these smoke rings, how they appear really. So the whole smoke, well, picture like this, yeah, can be modeled as a collection of entangled smoke rings. So there are several curves, like here, and these curves model you the behavior of the smoke, which is shown here. So what are these curves? So you have a velocity field here, of course, everywhere in free space. So, and it is uniquely determined by its vorticity, and vorticity is just curl of V, or rotation of V. So usually you learn this either at school or at the university at the first semester. Yeah? So what is this? So this is a vector, and it can be computed explicitly when you use V. It describes you have a velocity field here, and this describes your infinitesimal rotation of this velocity field, this omega. And the main point is and this is the main observation, that vorticity is localized along the curve. So this velocity field behaves well in a smooth way, but the vorticity is localized. And then you have these curves where the vorticity is localized, but you also have this velocity field, and this velocity field moves your vorticity curves. So this smoke ring is just a curve where the vorticity is localized and it is moved along with the flow. So if gamma is a curve that depends on space variable, parameter along the curve, and about time variable, then the equation which describes this evolution is written here. The derivative with respect to time is the cross product of the first derivative with respect to the space variable, arc-length parameterization of your curve, times the second variable. It is known as Hashimoto flow, Hashimoto curve, and it's known that it's integrable. Geometrically, the curve moves orthogonal to its oscillating plane. Yeah? So you have your curve, you approximate your curve by a plane, and then there is an orthogonal direction, and the velocity of this motion is equal to the curvature. So that's actually what this formula is about. So we describe this evolution. If you have a circle, then the curvature is constant, and then the circle moves with constant speed, and that's this standard smoke ring motion. But if your curve is not a circle, then it's more complicated. Okay, now let us discretize. Now our curve has points and has edges, and we mimic this arc length parameterization by saying that all the edges have the same length. So we take polygons, non-planar polygons with this property. And that's our curve gamma, and we consider first a discrete tangent flow. So how this point moves when our curve goes in the tangent direction. In the smooth setting, it will be the same curve, just differently parameterized. In the discrete case, it will be a sort of rotation of your curve, even for the circle. So you would like to, for this curve, for this flow, to preserve the arc length parameterization so that all the h lengths are preserved and are equal to 1, and then you end up with this formula. So this, I should say, this is the most difficult part of my talk. Yeah? So I am going to explain you a couple of formulas, and then it will become more elementary. So there is a discrete tangent flow. It's a sort of rotation of your curve. Then we can describe discrete smoke ring flow. That's the flow which you see here in this picture. You see the curve moves orthogonally to its plane, and it changes its form. Yeah, so that's the flow which you see in this picture. And then it's the same formula, but the orthogonal direction to two edges is given by the cross product of these two edges. And this is some normalization constant which comes exactly from this integrability theory, namely from the condition that this flow, the smoke ring flow, should commute with the tangent flow which we have defined previously. So, and these are two combinations, two flows, the smoke ring flow and the tangent flow. So now let me show how it works in reality, this discrete smoke ring flow. So that's the evolution which you obtain. Yeah? So that's your original curve. It evolves to this curve, and these are just various discretization steps. So that's a discrete smoke ring evolution described by this discretable, integrable, by integrable discretization. Okay, now let us come back to the picture which we have seen already, and now I am ready to explain you these formulas we have started with for the curvature and for the bending energy. Namely, in the classical theory, it is known that elastic curves can be characterized in a rather sophisticated way. You have a curve, and then you apply to this curve this smoke ring flow, or a combination of the smoke ring flow with the tangent flow. And look what happens to a curve. Typically, the curve will be deformed, but there is a class of curves that are not deformed, and they evolve by this rigid motion. So you have maybe a rather complicated form, but the form is preserved, and what happens to a curve? It moves by Euclidean motion under this linear combination of two flows. And the flows, the curves that satisfy these conditions are exactly the elastic curves or elastic rods. So what you can do now, you can say, okay, I define discrete elastic rods as discrete curves that stay invariant, that their form stays invariant with respect to the linear combination of these two flows. And that's the formula which is written here. This is a linear combination of the flows, and this means that this is a rigid motion of your curve. And if you give just this definition, then you end up with the formula for the curvature we have started with. You remember this tangent phi over 2 formula, and for the formula, with the formula for the bending energy, and that's it. So you see, it's not quite trivial to come to these formulas, but if you are doing structure-preserving discretizations, then you obtain these formulas and pictures that look pretty real. Okay, so again, applications. So of course, as usual, yeah, when you develop mathematical theory, it's nice theory. You can prove theorems. You can suggest very nice definitions. But when you go to applications, then you should do a little bit more. In this case, it's also true. So to make it practical, several features have to be included. For example, there should be interaction between vertex rings and the interaction with obstacles. And then this means that you should incorporate some more mathematics and maybe a little bit more theory. So what we see here in this picture is a smoke animation with DreamWorks, Megamind, and this was a joint program from Pinkel and Weissman with DreamWorks. And this smoke here was produced by using this technique. Maybe I will show you one more picture. So what you see here is this smoke, and it was made really by using this technique I have explained. Okay, you may say, okay, I can make this smoke easier, yeah? So somehow, yeah? Well, so do you need this complicated mathematics to make such a picture, yeah? So of course, yeah? So it can be made easier, but you would like to have it structure preserving. This means, in particular, what would you like to do? You would like to be able to edit this smoke. And how to edit the smoke, yeah? So if you have such a picture, how to change it? So in a way that it is still smoke, it still looks real. And this smoke ring approach allows you to do this. Because what you have finitely many curves, and you have finitely many data on these curves. And you can move these curves as you want. And finally, what you see at the end of the day is such picture, and that's how you can edit and model it. So it's quite practical thing. Okay, so now let me pass to other applications. So, and now we go to differential geometry or to discrete differential geometry. As I have explained already, so discrete differential geometry, the goal is to find, if you want, some polyhedral models for surfaces, maybe not polyhedral, more complicated, but also discrete, that keep structures of your smooth theory. And you are aiming at development of big theory. In principle, instead of differential geometry, it will be called discrete differential geometry. And then you know what is discrete curvature, what is discrete geodesic on your curve, what is a discrete curvature line. All kinds of notions that are known in differential geometry should be and can be naturally discretized. But it's a young theory, and we shouldn't expect that everything is already known. Imagine, so classical differential geometry was developed by great mathematicians. Almost all mathematicians you know have contributed into its development for many, many years. So we should wait a little bit until the complete theory is developed. And this is, of course, a theory also on the border between computer science and mathematics. So I'm more interested in mathematical part of this. But as I said, there are interesting applications. This is one of the applications which is, I think, or was rather unexpected. So here you see a sort of piece of a free-form architecture. It's a building, it's a real picture. It's not virtual reality, it's real reality. And it's a triangulated surface. These triangulars will be modeled with pieces of glass, and the edges are made out of steel. So if you would like to, if you're an architect, yeah, then of course you come to scientists or to engineers and say, okay, I would like to build that surface. Yeah? So, and you know quite well that it should be exactly this surface, not another one. Yeah? So, and then scientists come to you and say, oh, okay, great theory, and I can describe this surface. So that's not the surface the architects want. Yeah? So they want to discretize an arbitrary surface, the surface they want. So, and then what are the features that are important here? First of all, your surface should be as smooth as possible. Of course, it should be defined. And this is a big issue now to find out what are the proper definitions for smoothness of polyhedral surfaces. And also, you see sort of parameter lines here. Yeah, I show them to you. Yeah, so and they are also supposed to be smooth. Yeah, and not going to the left and to the right. Yeah, so if you construct a surface of that kind, it will be ugly, and this is not what people really want. Okay, so that's about the size of triangles and about the thickness of the edges. And this is one more piece of modern architecture. So the difference is that here you don't see triangles, you see quadrilaterals. And quadrilaterals are more practical if you are thinking about pieces of glass. So usually when we look around, then all pieces of glass we see are rectangles. Yeah? So, and of course, what you would like to do, you would like to model arbitrary surfaces with quadrilaterals and not with triangles. These quadrilaterals are not necessarily quadrangles. They may deviate from quadrangles. They may be more or less arbitrary quadrilaterals. But the question is how to build surfaces from quadrangles, quadrilaterals. And this is also a real example where you see that the problem is not that easy. Here, for example, on the top, you see that the pieces are almost rectangular and they are quadrilaterals. But when you go to the piece of a surface which is curved here, then these quadrilaterals are split into triangles. And the reason for this is that if you, for example, take this quadrilateral, then it's not planar. And you can't make non-planar quadrilateral out of glass. Okay, you can, but it's pretty expensive. Yeah. So therefore, you triangulate, and then it looks not optimal. So an appealing problem is how to approximate an arbitrary surface by planar quadrilateral nets. And you see that it's more or less obvious that this problem is not simple, because at every vertex here, you have 4 neighboring quadrilaterals. And for neighboring quadrilaterals means that you have 4 planes. And these 4 planes intersect at one vertex. And this is already an incidence. So 3 planes always intersect in a vertex. But 4 planes do not generically. So here they must. So this means that you cannot locally deform your surface. And so you should solve this problem globally. Well, the problem is serious. I remember a story. So at some point, some time ago, architects came to us and they said they had a problem. And the problem was 19 centimeters big. So because they were modeling these such surfaces piece by piece, yeah, gluing quadrilaterals together, but then at the end you see there is a gap, and it's not clear what to do with this gap. Yeah? So because you cannot deform locally, you should deform globally. Of course, you can solve all these problems, and they are all solved nowadays, but that's a practical problem. Okay, the problems can be even more complicated if you consider structure. And usually, I don't know, maybe not in India, but in Europe, we have double glazing. So 2 glasses. So because of the temperature difference of outside and inside. So, and then it means that you have 2 surfaces. One surface here from one side, and one surface from another side. And both should be comprised by quadrilaterals, and these quadrilaterals should fit together. Even if you don't have second surface, then maybe you have such structure, but also you have layers that are supposed to be planar. So, and then you come to the following constructions. That's a real construction, how these edges are glued together. And that's a mathematical picture which describes you what is the goal, what kind of structures you would like to get. So these are not the pieces of the glass, but the pieces of the steel. So they are your edges. And from the top here and from the bottom here, you have pieces of the glass attached. And you would like to have here them all meeting at this point, and on the bottom also all 4 pieces meet at one point. So, and this is already a condition for this. So it is called so-called conical nets. They are a little bit more complicated. This means that 4 planes must have a common touching sphere. That's a condition, an extra condition for this for every vertex. These conical nets were also introduced quite recently, by Potman, and nowadays they are already used in architecture. So it's purely mathematical structure, an integrable structure actually, yeah. So but is already practically used. So let me show you a picture. So of a surface where all these conditions are satisfied, you have edges of constant width. You have 2 surfaces from one side and from another side built of quadrilaterals. They're perfectly glued together. But this surface is actually this one. It's a mathematical surface. Maybe some of you can recognize the famous Schwarz surface, which is a minimal surface. It's a model for soap films that minimize the area of the surface. So and here it's just the upper half of this surface. And it can be in principle used for architecture, but not very practical because of the rain. But you can imagine, you can ask these questions, how to build such nets, how to build for arbitrary surfaces. So this is already very interesting mathematical problem and very interesting practical problem. So these pictures were virtual, and now I'm going to show you a real picture. That's if you are in Paris, then go to the Eiffel Tower and to the first floor. And quite recently, there were 3 pavilions built here. with curved glass windows or walls. Yeah, so that's the picture from there. So this glass is not planar; it's curved, and it was constructed by the same technique, applying these conical nets by Portman, and these are real surfaces which you can see here. So the method is to apply conical nets that are integrable systems, actually. Okay, so now I'm going to give you one more example of this structure-preserving discretization, and you can see it here. It's about parameterization of surfaces. Here we have two particular surfaces of genus 1 and genus 2. This means with one hole and with two holes. And here we have so-called conformal parameterizations. So what I'm going to do next, I'm going to show you a movie which was recently made and recently published by Springer. So you have heard already about this. It's a movie about conformal maps. And at the end of this movie, you see a little bit, a small piece of this mathematical theory that is new and which is about this structure-preserving discretization. So all the pictures were made using this theory, but of course we made this movie for with Charles Gunn for a broad audience. Yeah, I'm quite happy that there are so many here. So so now it's a very easy job for me. I will just let you watch the movie. Okay. So and I will answer your questions after that. Yeah. So but first, let us switch to the movie. So, as I said, it's a movie about conformal mappings, and everything will be explained here. So it is supposed to be self-explanatory. So.
As long as the Earth was flat, mapmakers had it easy. By scaling the actual dimensions uniformly in all directions, they could produce accurate, flat maps of the Earth, easy to print, fold up, or bind into atlases. When the round Earth, however, rolled around, life became harder. Shrinking a sphere, or a piece of a sphere uniformly, produces a smaller sphere or piece of a sphere not easy to print or fold up. This movie tells the story of how the search for a good way to make flat maps of curved surfaces had important consequences for mathematics. Our story begins during the Age of Exploration. In 1569, a Flemish mapmaker published a world map with the title, A New and Improved Description of the Earth Adapted for Use by Sailors. His map was a technological innovation of the first order and made him famous under his Latinized name, Mercator. We show it here, blended with modern satellite imagery. What is special about Mercator's map? To begin with, circles of constant longitude are mapped to the vertical lines on the map, while circles of constant latitude appear as the horizontal lines on the map. Thus, the cardinal directions, north, south, east, and west, always appear on the map as up, down, right, and left. But that's not all. All intermediate compass directions are shown correctly on the map, a very useful feature for ocean-going navigation. In fact, Mercator's projection is the only map projection with these properties. Although distances are distorted as one moves north and south on the map, angles are always correctly shown. A map that preserves angles is called conformal. Conformal maps have turned out to be of fundamental importance in mathematics. This movie presents highlights of their development since Mercator's time. One of the simplest conformal maps is stereographic projection, in which a sphere resting on a plane is projected onto the plane from the top point of the sphere. This example makes clear a characteristic feature of conformal maps we already met in Mercator's projection. While angles are preserved, distances are not. Another rich source of conformal maps is provided by functions of a complex variable. For example, the complex exponential function. The complex sine function. The complex squaring function. The complex reciprocal function. And a complex theta function. Let's return now to Mercator's map. Although no one knows exactly how Mercator produced his map, mathematicians later showed it can be explained using two conformal steps. First, the sphere is flattened out onto the plane using stereographic projection. Here, a magic brush performs the projection from the sphere onto the plane. The part of the globe covered by Mercator's map is projected onto a large ring in the plane. In the second step, this ring is unwrapped onto a rectangle using the complex logarithm function, the inverse of the complex exponential function. In the title sequence, we saw that every letter could be conformally mapped onto a rectangle. Is it always possible to find a conformal map between two shapes? Riemann's mapping theorem from 1851 asserts that any connected region without holes that isn't the whole plane can be mapped conformally onto any other such region. How many such conformal maps are there? To answer this question, consider conformal maps from our chosen shape to a disk. We may choose any point within the shape to map to the center of the disk. The conformal map is then uniquely determined up to a rotation of the disk. Similar results hold for planar regions with holes. Such regions can be mapped conformally onto regions bounded by several circles. Up till now, we have considered conformal maps of planar regions. We turn now to consider conformal maps of closed surfaces in three-dimensional space. This inflated letter C, for example, maps conformally onto a sphere. Here, we rotate the globe while holding the letter fixed. Notice that the two arms of the C behave like magnifying glasses. A conformal map to the sphere is determined by choosing any 3 points on the original surface to map to any 3 points on the sphere. The resulting family of conformal maps can be visualized either by moving the 3 points on the original surface or the 3 points on the sphere. Not all closed surfaces can be mapped conformally onto a sphere. This inflated letter A, for example, has one hole. Such a surface is called a torus. A torus can be cut open along two closed curves sharing a common point, so that the cut open surface maps conformally onto a parallelogram, in this case a rectangle. The position of the cutting curves on the surface is arbitrary. They can be moved without changing the rectangle. We now replace the original checkerboard pattern with a design that more clearly reveals the translational symmetries of the rectangle. We see the top and bottom edges can be translated onto one another, as can the left and right edges. In fact, translated copies of the rectangle cover the plane without overlap. In this way, every torus can be unrolled conformally onto a tessellation of the Euclidean plane. A closed surface can have more than one hole. This inflated letter B has two holes. Such a surface is called a two-holed torus and can be cut open along four closed curves sharing a common point, so that the cut open surface maps conformally onto a hyperbolic octagon, a flat region bounded by 8 circular arcs. This octagon also has translational symmetries, but the translations are hyperbolic, not Euclidean. The hyperbolic plane appears here as the unit disk. In this way, every two-holed torus can be unrolled conformally onto a tessellation of the hyperbolic plane. We saw that it is possible to map a square grid conformally onto the inflated letters C and A. Can we do the same for the inflated letter B? The answer is yes, but it's more complicated. The surface can be cut open along a set of 5 curves so that it maps onto the flat region on the right, where, as before, parallel boundary segments of the same color can be identified with Euclidean translations. This map is conformal except at 2 special points called branch points of order 2. Since 3 cutting curves meet at each branch point appears 3 times on the boundary of the flat region. the branch points are said to be of order 2, since at these points, instead of preserving angles, the map doubles them. The history of conformal maps does not end here. In the past few decades, a new theory of discrete conformal maps has been developed for surfaces consisting of polygons, such as this triangular mesh. A map between two such surfaces is said to be conformal if it's possible to assign a scaling factor to every vertex so that the length of an edge in the image surface is equal to the length of the original edge times the scaling factors at its two endpoints. When the triangles become very small, the theory of discrete conformal maps converges to the classical theory. In this way, all the images of the classical theory shown in this movie were produced using the discrete theory. The discrete theory of conformal maps is finding applications in fields such as computer graphics and architecture. We hope you have enjoyed the story of how one simple question, how can you make good flat maps of curved surfaces, led to the discovery of conformal maps, and how this developed into an important and still thriving branch of mathematics.
Okay, so this movie was actually translated into 6 languages already, and I just learned that the poster of my lecture was translated in 2 Indian languages. Yeah? So if you want, you may do this with the same with this movie. Please let me know. Okay, and so that was an example of discrete theory that was applied to the theory of conformal mappings, and here you see that it's theoretically quite interesting and quite deep and practically quite useful. So, and maybe I have just 1 minute to finish my talk, and I would like to mention that there exists one more movie with the same title as my talk, which is called The Discrete Charm of Geometry, but this is not an animation movie. It's a movie about mathematicians and about how they work together. It's a 65-minute movie, which is professionally made, shown in cinemas, had some awards, and it was made by Ekaterina Remenko, so that's her email address. You can contact her if you would like to see this. And I would like just to give you one reference. So it was written not by a famous mathematician, but by somebody who watched the movie, and it was very interesting for us to see this, that if you gave up a career in mathematicians, it could be that you are green with envy afterwards, yeah, if you watch this movie. Yeah? So please do mathematics and be convinced that it's a good thing to do. So we are convinced, and I hope I gave you a couple of examples showing that mathematics is interesting and is practical. Thank you for your attention. So now questions, yeah? No?
So I guess before we start with the questions, I have just two announcements. One is the date for next Kaapi, which I've actually forgot, at 19th August. And it's on the, so I guess you, yeah, I thought you were going to put the,
Yeah.
is it? Oh, but this is your computer, so no, it's okay. Yeah, so that will be, and anyway, it's on the Facebook. It's also on ICTS webpage, the announcements for next talk. That's one announcement. The second one is we just sent a questionnaire to the people who are on the mailing list of ICTS. So some of you probably have received and maybe responded to the question already. If you haven't received the questions from us, then you can please sign up. So usually there is a place to sign up. If you are not receiving our emails and if you want to receive emails about ICTS events, then please sign up and you will receive regular emails from us about ICTS events, including the question we sent today about, well, which was about mathematics. And the third announcement is we would really like to acknowledge Gubi Labs for helping us with translating. Actually, they translated the posters into Kannada and Hindi. This was an experiment that we started, so hopefully we can continue it over, now continuously for all the talks in the future. So thanks to Gubi Labs for that. Okay, I think that ends the announcement. And so we can now take questions. So I guess you know the drill. There are microphones there. One is over here and one is in the middle. If you go to the middle, we can still hear you, but you will not be on the camera. But apart from that, we can still hear you. So please go to one of the microphones to ask questions. Yes? Wait. Oh. Was there somebody there? No? Okay. Or if you're too shy, then we can bring a microphone to you if you raise your hand.
Okay.
No?
I mean, can I ask a question?
Okay, yeah, sure, of course, yeah.
You had mentioned about a complete unified discrete theory. Does it also correspond to the, in computer graphics, like I'm talking about dynamics, the computational speeds can be reduced, like optimized using that model which you are talking?
So which model are you talking about?
No, I'm taking your, that unified discrete theory which you had mentioned about. Does it easily translate into, like in computational speed terms also, it optimizes the processing speed?
Computational speed, you mean, yeah?
Yeah.
Well, we are doing theory, and but I think this theory is useful for computations, because first we can prove theorems like about convergence. So because usually people just do computations, and this convergence result, mathematical convergence results, are difficult. For conformal map, not exactly in this setup as I have shown here, but for similar setups, you can prove that convergence is C-infinity convergence. So that's already a good thing to know. So as far as computational speed is concerned, then our observation is, well, you can model surfaces with same structures or objects with the same structures by using just less points, yeah, which of course is essential for the computational speed.
Okay, thank you.
Other question?
In this movie, when you made these conformal maps for various figures, surfaces and all, did you use any particular software tool, or you generated your own code and wrote it?
It's our code, yeah. So the software development for this movie is Stefan Zehelman, and he has developed software which is called VeryLab, It is to minimize various geometric functionals when you are dealing with discrete surfaces. So in this functional we are using here, it's a rather sophisticated functional based on dilogarithm function. It's just one example of application of his software, but it's software which was developed in our group. So you can use it, yeah. So it's available online, yeah. So if you are interested, just contact him, yeah, and you can. It's Java based.
Yeah. Hello, sir. Sir, you were talking about the discreteness in the figures, like geometrical figures. So what do we mean that, like the things which are visible discrete to our eyes, or what a figure is a continuous thing. So what do we say when we are saying that the figure is discrete?
So it's not discrete field. We discretize space variables. So instead of smooth functions, we are using functions that are defined on a lattice. We are using lattices. These are the maps from, in this case, from something like Z2, from the square grid, to 3 space. So that's what we mean by discretization.
Okay, so in
but we do not discretize the image.
Okay, so in like a simple language, we can say that we can count the surfaces of our figure.
So sorry, could you please?
Like discreteness means we can count the things. Like
yeah. There are in all these examples. Actually, there are finitely many points, but you can work with planes. And use countedly many points, but it's always countable.
Okay.
Yeah.
And sir, you mentioned about Biot-Savart law in smoke ring model.
Sorry, yes.
You mentioned about Biot-Savart law, like you derived.
Okay. There was.
So, but it relates with the magnetic field. So how the thing coming in our smoke field?
So these are the classical formulas that allow you to recover the velocity field from the vorticity field. So actually you have the vorticity field, but if you know it, and that's your smoke rings, where your vorticity is concentrated, then there are explicit formulas that allow you to recover the velocity field in the whole space. That's how we work, how Pinker and Weissman did that. So you need some regularization. But that's how the formulas were used.
So can I quickly make a connection? The same, I mean, what applies in magnetism also applies for velocity fields and vorticity. So maybe we can discuss later. It's not only for magnetism, the Biot-Savart law.
Okay, yeah. Thank you, sir.
Can this theory be used for structural analysis also? What forces are acting on which members in this?
For which analysis?
Structural analysis. What forces are acting on which members? You mean when the structure is created with a lot of surfaces here, right?
Okay, physics.
And, yeah, it's actually about
Well, it has been done actually already. It's also by a group of Potman. So, and the question can be set up in the following way. So, an interesting question. I think it is close to the question you have mentioned. Yeah. So, you have a surface. It has planar faces. And also, but it is under gravitation field. And then there are forces along the edges, and these forces are established in such a way that the sums of the forces at every vertex are vertical and are equal to the gravitation field. It's balancing. Yeah? So, and this means that if you build your surface out of maybe thick quadrilaterals and put them together, then it will stay and will not destroy. Yeah. So, and there is a nice paper about this from the group of Potman, where they simply, they don't build real models, but they do build virtual models, and then you can just delete one quadrilateral, but the surface stays. Yeah. So, but if you delete a little bit more, then it drops down. Yeah. So, but that's exactly a further development along the lines of discrete differential geometry.
Are there any applications of discretization to Navier-Stokes fluids or any other ideal fluids, just to match it with the continuum?
So there are many flows, of course, yeah, which have been discretized. Well, I don't know what I should really mention here, but okay, there are problems like discretization of the mean curvature flow. So what happens to your polyhedral surfaces? Well, also discretization hydrodynamics, preserving structure-preserving discretization, and in electrodynamics. It is known under the name, so you may search discrete exterior calculus. So that exists. There are many papers about this. So, but this theory is essentially a linear theory, which is deep theory, but slightly simpler than the theories we were applying, but because these theories are nonlinear.
Yeah. So,
excuse me, sir. Here, sir.
Yeah.
In the map between.
Oh, sorry. So just yeah. Go ahead.
So the thing is, when I take a complex plane,
yeah,
and when I do a stereographic projection on a Riemann sphere, so what happens to the point of at infinity?
So you take a complex plane.
Yeah. So when I do a stereographic projection,
yeah,
onto a sphere,
yeah.
So how do I interpret infinity that time? The point at infinity.
Well, in our case, the relation between the plane and the sphere is the stereographic projection, yeah, which you have seen in the movie. So it's a conformal map, preserving all conformal properties, and then the point at infinity becomes the north pole of the sphere. So that's. So
how do I interpret that? Like, if an infinity becomes a point on the sphere, how do I interpret that? Like, the infinity becomes a north pole, right?
Yeah.
How do I interpret that? Like, infinity becoming a point.
So, this means that the plane compactified with the point at infinity is conformally seeing the same as the round sphere. That's the interpretation. And for example, one important property of the stereographic projection is that circles on the plane are mapped to circles on the sphere. They do correspond. But if you take this distinguished point at infinity, then circles passing through this point are just straight lines. And this means that straight lines are mapped to circles passing through the north pole of the sphere. So that's one of the ways to see this mapping.
Yes, please, go ahead. There.
So in the map between the spinning top and the elastic rod, what exactly was meant by the energy of the elastic rod?
The energy of the elastic rod, okay, let us first talk about elastic curves. So this means that you have bending, but you don't have twist energy. So for the bending energy, in the classical case, you integrate the curvature squared along the curve. So in the discrete case, as I have shown to you, the proper definition for the discrete curvature is just you take two edges, take the deviation angle of this edge, take a tangent of phi over 2 of this angle, and take it twice. That's a proper formula for this discrete curvature. So there is a similar formula for the torsion that appears from this theory, but it's more complicated and I haven't presented it here. If you want, you can look at my paper and I can give you a reference. So for the classical elastic rod, you make a combination of these two energies. The bending energy is curvature squared integrated along the curve, that's this bending energy, and the twisting energy is you take the torsion of the frame, of the physical frame along the curve, and then integrate the square of the torsion. So there is a formula for the discrete torsion, and when you take this formula, then you end up with discrete energy coming from this theory. It will be a linear combination of discrete torsion and discrete curvature.
And what is the quantity analogous to that for the spinning top?
Sorry?
Analogous to the energy of the elastic rod due to bending and twisting. what do we get for the spinning top, since there's a map between the two?
It will be the same energy. The energies coincide. For the elastic, for the spinning top, you have kinetic energy and potential energy, and these two energies together will give you the energy of the elastic of the spinning top. Actually, the difference will be the Lagrangian function of the elastic of the spinning top. And the Lagrangian function, the minimization of the Lagrangian, or critical points of the Lagrangian, describe you the trajectories of the spinning top. So you take this Lagrangian and differently interpret it, it will give you this energy, bending plus twisting energy for the elastic rods.
So does the map between the...
So maybe we can have some more questions over the coffee, please.
Okay.
There's time, there will be lots of time over coffee, so we can go to the next person.
Okay, I will be happy to give you a reference and give you
if
the
you hang
formulas.
around after the talk and just wait for a few minutes. Yes, please.
Yeah, the question I have is, can we use this theory to build, I'm here. Yeah.
On this side.
Ah, I see, okay.
Yeah, can we use this theory to build artificial human organs? For example, let's say prosthetic limb or something that needs...
What do you want to model? Artificial?
The human organs?
Ah.
Artificial limbs.
Well, it goes beyond my knowledge, yeah. So, so maybe I would be happy if it would be applied, but I don't know.
Sir, I have a small question. To your right, sir.
Excuse me, sir.
Yeah.
Sir, if we are considering 2-3 complex planes, for examples U, V, and W plane. So if you want to convert from one plane to another, like conformal mapping, whatever we saw in the movie, can we convert like simultaneously while we are converting the plane, conforming, like when we are creating a conformal mapping from U to V and V to Z, can we do simultaneously like that? Like if I am changing U, and is there, can I change V and Z simultaneously by any relation to that?
So, okay, it works. Yeah. So the composition works here. So because, well, let me repeat you the definition which was shortly shown at the end of the movie of discrete conformal maps. So you take a triangulated surface. It is not necessarily a piece of a plane. It shouldn't be necessarily a plane. It's just an abstract surface. Can lie in free space or can be just a set of polygons glued together. So then a conformal mapping means, a conformal change of this surface means you choose one vertex and multiply the length of all the edges adjacent to this vertex with the same factor. So if you do this, you end up with a mesh that is called discretely conformal equivalent. Of course, you can do this at all vertices simultaneously. And that's the definition. Of course, it's, this definition is invariant with respect to compositions. Yeah? So you can take U plane, V plane, W plane, take conformal factors here, here, and here, and they will be just products. Yeah? So for this map.
So is this theory only applicable for elastic materials only, or it is applicable for all the inelastic materials?
Well, the last theory has nothing to do with this, of this conformal mapping, has nothing to do with elasticity theory, at least for the applications we have mentioned here. It's just discrete complex analysis. Yeah?
Hello. Yeah, so my question may be a little basic or dumb. But initially we talked about that the map of the entire Earth was created as plane from a sphere. And at that time they choose to keep the angles same, but distances are not represented correctly. Versus there are other option when distances are kept correct, but angles may distort at that point, right?
Okay.
So what are the pros and cons of each approach? Why they choose this but not this? If they do other way around, what will be the problem or something? Yeah.
Well, very good question actually. Yeah? So, and that's a good point. So in the classical case, of course, you have many properties. So, and you would, you should fix which of them should be preserved in the discrete setup. You cannot preserve them all. So, and of course, conformal means angle preserving, the conformal map, and you would like to preserve angles. And that's not what we are doing in this approach. So this approach means that we are based on the metric notion, on notion of the metric, and we are looking at conformal changes of metric exactly in the sense as I have told you. So you choose a conformal factor at a vertex, and this is sort of homogeneous scaling, homogeneous in all directions at this point. And you can change these factors at all the points, so they may be different, and but they are homogeneous at all the points. And it turns out that it leads you to rich theory, so really, which is related to hyperbolic polyhedra with points at infinity, with vertices at infinity, with a lot of mathematics. It gives you a convex variational principle, which you minimize, and you can do computations, and you can prove the theorems. So in this case, we are pretty sure that the definition we end up with is the right definition, and unfortunately, this property that the angles are preserved is not preserved for this definition, but you will get this property in the continuum limit. So when your discretization is fine, then of course your smooth map will be in the limit. Conformal means angle preserving.
Okay,
Maybe,
so one.
Maybe I was talking about the map of Earth.
Of what? Map?
So initially you said somebody created map of Earth.
Of Earth, yeah, okay.
And when he created a flat map, he chose to keep the angle same versus distance same.
Okay, okay.
My question was,
okay, I understand.
He could have kept the distance fixed, correct?
Okay.
Rather than angles fixed. So what is the pros and cons for that?
Okay, so you can't keep the distances fixed because then it's an isometry of your surface. And well, if you take a piece of paper, yeah, so this is a piece of plane. What you can do with this piece of paper, you can deform it like this. These are all isometries. But you can't make a sphere, round sphere of this, from this piece of paper. You should make cuts and should destroy it. So the curvature of the surface is preserved under these isometric deformations. That's a famous theorem by Gauss. So this means that there is no chance to put your sphere isometrically to the plane. So you should change different distances. Yeah. So the next question is, what can you preserve? And it turns out that you can preserve angles. And of course, these angles are quite useful for these maps, as if you are for the navigation, because this gives you a proper direction where to go. Yeah. So, but that's it. You can't get both. Yeah. Otherwise, you should stay on the globe. Yeah. So.
So there is a question from online live streaming. Yeah. How is the conformal mapping technique useful in describing fundamental nature of space-time?
Useful for what?
How is the conformal mapping technique useful in describing the fundamental nature of space-time?
Oh. Yeah. As I said, so, well, I just gave you a couple of examples, and this is the beginning of the theory. Yeah? So we are doing surfaces. So, of course, there are plenty of interesting questions, and there are people working on this. This theory will be developed, but I can't tell you about discretization results of our real space-time. So there are institute working on about this. Yeah.
A question over there. Yes.
I have one small question, sir. Sir, during your lecture, you said some architects came to you with the problem of 19 centimeter. So how did you, as a mathematician, help them to cover that?
Well, that was already a long time ago. I think now architects know what to do. Yeah. So, but it's a real thing, the real story. So they came to me because they knew that we are sort of interested in polyhedral surfaces, and they have already a polyhedral surface. It was a concrete project. Well, building a roof in the building. Well, there was a building like this, and in the center yard, they wanted to make a roof made out of glass. And of course, it should be built by quadrilaterals. and they were trying to do this themselves. And as I said, piece by piece, and then at the end you see that there is a gap, and you don't know what to do. So our first solution to this problem was quite naive and quite simple. You say, you can't solve this problem locally, so if you keep the rest of your surface, then you cannot solve the problem with the hole. So you should change the whole surface and just do the following thing. Approximate your surface, choose the points where they should be located, and then vary them all to satisfy all the conditions by using some variational principles. And now how these problems are solved.
Excuse me, sir.
Thank you, sir.
Excuse me.
Yeah, question over there.
So firstly, the shape of the hole does not matter, right? The shape of the torus does not matter it does not matter about the, that does not change the final shape at which that it conforms to, right? Sorry, I'll repeat my question. So you have the letter A and
letter A, yeah?
Yeah, and you have the hole.
Yeah.
It's a triangle, whereas
yeah.
in the letter B, it is kind of semicircle-ish.
Yeah.
Will that change the, or if you had the letter D, that's a better example, that's a semicircle. Will that change the shape of the 2D plane on which you can conform it to?
Mm-hmm. So, you have, if you have a letter B, you have a torus. And every torus can be obtained as a quadrilateral, a parallelogram actually, with identified edges, opposite edges identified. That's a conformal model for every torus. This means that if you are modeling letter A, then you are looking for a conformal map of a parallelogram to the letter A in such a way that the edges are glued together on the letter A. So in this case, because of the symmetry of the letter, okay, so there is of course a reflection symmetry, this quadrilateral is actually a rectangle. So in this case, the story is rather simple, but for the letter B, it's more complicated because, well, there is no conformal map of a flapped domain to the letter B without singularities. So you should choose 2 points on the letter B. It's the topological thing. If you take a square grid, then you cannot put it to the letter B in such a way that at each vertex exactly 4 quadrilaterals meet. So there will be 2 distinguished vertices where more quadrilaterals meet together. The question is where they should be located, and there is some theory which we have developed just to parameterize this letter B. That was fun, yeah. But there are 2 distinguished points. One of them can be chosen freely, but another one is then uniquely determined. You cannot prescribe them arbitrarily. So that's the story behind this letter B. So I think, pretty soon there will be a mathematical paper about this letter B. How to make it, yeah. So because it was a little bit involved, yeah. So and there is a piece of mathematical theory behind this, not only about the letter B, but about parameterization of closed surfaces, yeah.
Okay, and one more question. What happens when you have 3 toruses?
If I have what? 3?
3 toruses. If you have the letter 8 with another circle.
There is not such a letter in...
yeah.
So, actually...
genus 3 surface.
I don't know, maybe we should use the Indian alphabet, yeah? So, we can do with any number of holes, of course. It's a universal theory. It works for any. Yeah, so and also you can use hyperbolic uniformization that was shown for the letter B, or Euclidean uniformization with singular conical singularities. So, okay.
Yeah, one question over there.
Good evening, sir. In the movie, the animation where you were mapping the inflated alphabets, the letters to, say, a plane, You said that we could start with any 3 points and they remain sort of invariant. They look like fixed points. Is there a fixed point concept here? And if there is something invariant, what exactly is invariant about those 3 points?
Well, you are talking about these 3 points chosen on the sphere,
Yes,
yeah?
yes.
Okay, so the theorem is that there is a conformal mapping of a sphere to itself that maps these 3 points to 3 arbitrary points on the sphere. So you can make them arbitrary by conformal mapping.
Okay.
So this means this is just a Möbius transformation which is known explicitly.
Okay.
So and this means this freedom is always there. So if you have a map to the sphere that is conformal, then you can apply one extra Möbius transformation, mapping 3 arbitrary points to 3 arbitrary points. So that's the freedom which is always there, and you can fix them as you want.
Okay. Thank you.
Okay, so there are more questions, but I would like to kind of end this here, and then we can have questions over coffee, if you don't mind. There was somebody online who asked a question about Gaussian curvature and minimal surfaces as well, but I think I will defer it to, maybe I can send an email with this question to you later, so you can answer it online later. So thanks a lot for attending this talk, and let's thank the speaker for the excellent lecture.
Okay. Thank you very much for
coffee and more questions outside.
Okay, thank you very much for your attention. I was really happy to see so many young faces.